Hi, my name is Robert Hovden. I'm a professor in the Department of Material Science here at the University of Michigan. And our lab focuses on seeing the invisible worlds. We like to explore things smaller than light itself. So a lot of new technologies are being made at the nano and even atomic scale. Seeing things this small is very challenging because it's smaller than light itself. So what we do in our lab is use high energy electrons, where matter has wavelengths down to a few picometers. And this gives us the resolving power we need to see atomic structure and nanoscale technologies. And we can do this in 2 dimensions, we can even do it in 3 dimensions. So here is a material, the nanocubes used in clean energy applications that we've blown up 10 million times in size, and we've 3D printed it to understand how its nanoscale features impact the macroscale properties of this clean energy material. But we can go even smaller than this. Because our resolving power is at an angstrom, we can see the smallest bond lengths in nature. It means we can see atoms. We can understand how atoms arrange with each other and give us new functional properties.
My research is in developing new computational methods to visualize the 3-dimensional structure of nanomaterials, specifically using electron microscopes that could be able to use very fine electron probes to visualize the atomic structure of materials and be able to correlate these 2-dimensional images with 3D visualizations of its whole entire morphology.
Research starts with a conversation. My door is always open to talk about science, your interests, and what we do here at the University of Michigan. Students in my group at all levels have made notable contributions, from the undergraduate to the master's to the PhD. It's a very rewarding experience that I encourage you to explore.
One of the samples we look at is an iron oxide nanoparticle that is composed of a Wurtzite structure, which is used for catalytic applications. And we also look at gallium nitride 3,5 materials that's made of an FCC structure used for solar cell harvesting for retention of energy, electronic energy.
To illustrate the incredible resolving power of modern electron microscopes, the microscopes we have here at the University of Michigan, let me show you a picture of atoms. These are tantalum atoms, at least the bright ones are. There's also some sulfur atoms in there too. In this material known as tantalum disulfide, the structure of the material down to a picometer dictates its overall properties. These materials can have tiny picoscale distortions that change the material from a metal to an insulator. And so by controlling these picoscale distortions, we aim to create the future of electronic devices. My lab and myself are deeply interested in understanding how atoms arrange, seeing atomic structure at the length scales which they interact. And by understanding matter and the arrangement of matter, we hope to solve the future of society's problems, from clean energy to computation.